Why, hello, advanced geometry students. It is I, Mr. Donaldson, and I'm back today to talk with you about section 6.1, which is tangent properties. Hopefully you recall from yesterday's notes from section 1.7 that the definition of a tangent is a line that intersects a circle at exactly one point. And I also should point out that that line needs to be coplanar with the circle for that definition to hold. So, the first thing I'd like for you to do today is to pause this video and do this warm-up if you have not done it already. And then when you're done, come back and check your answers as just a quick way for you to gauge if you understand the vocabulary so far about circles from section 1.7. Oh, hello. Welcome back. All right, here we go. Let's take a look and see what you got. So first one is congruent circles. So you guys, congruent circles by definition are two circles with congruent radii. And you can see that that would be option F. You have two circles, each radius is 3, so there we go, they are congruent. Concentric circles by definition are coplanar circles that share the same center. And you'll notice that option E has two circles. You got the smaller inside circle, this bigger outside circle, and they have the same center. So that would be option E. A radius is a segment that goes from the center of a circle to any point on the circle. So just looking at my different options, it's definitely either going to be A, C, or D, because those are the only options that are segments. And then which one of those goes from the center? Looks like segment OE. So it looks like C is going to be the solution to that. All right, next is a chord. Again, a chord is by definition a segment. So again, I'm limited to either A, C, or D, whose endpoints are on the circle. So really it looks like I have two choices here. Segment DC is a chord, and segment AB is also a chord. But if you look ahead and you see that diameter is a choice, I'm going to save segment AB for diameter. So the chord I'm going to use is option A, which is segment DC, the segment whose endpoints are on that circle. And then next, diameter is a chord, so also a segment that contains the center. So that would be segment AB or option D. Next, as I just told you a second ago, a tangent is a line. I mean, honestly, I don't have to really do much work because there's only one line on here. It's B. By definition, it's a line that intersects a circle at exactly one point, and you'll notice there's only one option there. That is line TG. So that would be B. Next, a central angle. Kind of the same thing we just talked about with tangent. There's only one option. If you look at all these different options, there's only one angle here. So that's obviously got to be the answer. But just to confirm, a central angle is an angle whose vertex is on the center of a circle. And check it out. Angle PTR is a central angle. So that J would be the answer. All right, next is a minor arc. Again, we're very limited to our choices because by definition, a minor arc, in terms of how you name it, you only name a minor arc with 2 points. And look, G is the only one that has an arc with 2 points. But a minor arc is less than half the circle. So arc RQ goes from R to Q. Because it's only 2 letters, I know it's the shortest way around. It's a minor arc. So that would be G. Next, a major arc. A major arc is an arc that is more than half the circle. So it's either going to be H or I because you name a major arc with 3 letters. So let's just take a look. PRQ is half the circle. And then PQR, from P through Q to R, that is more than half the circle. So PQR option H would be the major arc. And then the semicircle is half the circle, and that would be, oops, I think I did that one backwards. Excuse me, my major arc should have been PQR, which was I. And then my semicircle is half the circle, which would be PRQ, which is option H. So the purpose of that, you guys, just a quick run through. Do you remember the vocabulary? Pretty important that you know the circle vocabulary. All right, so now that we remember the vocabulary, let's just kind of go back, or I guess go forward. We'll talk about some properties or theorems that are true about tangents. So this first theorem, as you can tell, was not very creative with the name, the tangent perpendicular to radius theorem. You guys, these names are not set in stone all across different texts. You know, this is just what the textbook, our textbook's author calls this theorem. So tangent perpendicular to radius theorem simply says that a tangent to a circle is perpendicular to the radius of the circle at that point of tangency. So when I see this drawing and I know that these, and this is an assumption you guys can make as well, if I give you a line that looks like it's tangent, you can assume that it is. I'm not going to try to trick you. So what I would do in this diagram, I would just based on this theorem, is I would draw my radii, and I know that any radius in a circle would be congruent to any other radius. The radii of a circle are congruent. I would mark them congruent, and then based on this theorem, I would mark the radius perpendicular to the tangent. So when given diagrams of circles and or tangents, always draw radius, draw radii, and mark them congruent, and mark the radius, and my handwriting sucks, sorry, and tangent perpendicular. Do that every time. All right, let me show you an example of why that's helpful. So here we go. In this diagram, line ED is tangent to circle N, and NA is congruent to AD. So I'm going to go ahead and mark NA being congruent to AD. And based on the tip I just gave you, I'm going to draw my radius. I'm going to mark it congruent to this radius. Now this radius had 2 tick marks, so this one needs to have 2 tick marks as well. And then I will mark my tangent and radius perpendicular to one another. So here's what I know in this problem. I know that NE is 5, and it wants to know ND. Now remember, when there's no notation, no line, no segment, no ray above, it's the distance from N to D. So the distance from N to D would be, well, if this radius is 5, this radius is 5, and NA is marked congruent to AD, so this would be 5 as well, so ND would be 10. The next thing says if the measure of angle ENA is 55 degrees, ENA, 55 degrees, find the measure of angle ADM, this angle right here. So what I'm going to do is I'm going to use the triangle sum theorem first, and so here's the triangle I'm referencing. And I know that all the angles in that triangle have to add to 180. So if this is 90 and that's 55, that's 145 degrees, which leaves 35 degrees for this. And then these two angles, angle EDN and angle ADM, are a linear pair. And we know that by the linear pair postulate, they have to add to 180 degrees, which makes 145 degrees for angle ADM. So that problem was pretty easy once we drew that radius and once we marked it congruent to the other ones and also marked it perpendicular to the tangent. All right, guys, so the next thing is the tangent segments theorem, and it says 2 tangent segments from a point outside of a circle to the circle are congruent. And so what I'm talking about here is I've got a circle, I've got a point outside the circle, and these segments from P to O, and from, I can't even talk, I think that's a Q, and from Q to O would be congruent to each other based on this theorem. The reason I call it the ice cream cone theorem is because it kind of looks like an ice cream cone. And the sides of that cone are congruent to each other. Oh, me. There's my ice cream. Oh, man, look at that. Oh, yeah, cherry on top. Boom. All right, ice cream cone theorem. So what I'm going to do here is I'm just going to very informally, using a flow plan, prove to you why that must be true. So the given is that segment OP and segment OQ are tangent to circle, I don't know what that is, maybe an I? I don't know. It's hard to see, they're pretty small. Alright, it's tangent to circle I. I want to prove that segment OP has to be congruent to segment OQ. And just as I have stressed to you a ton, you guys, this is all based on triangle congruency, so check it out. Now, this little flow plan looks a little weird, and here's why. The very first thing that I know are the tangent segments, okay? So OP and OQ, or QO, are tangent segments, or tangent to circle I. All right, now, what does that mean? All right, well, here's what I know it means. By the tangent perpendicular to a radius theorem, that means that OP is perpendicular to IP, and that OQ must be perpendicular to IQ. Bam, bam. Now, another thing, actually, I should probably put a little rectangle here. Oops, check this out. One other thing I got to do, because you could tell by these three little boxes, we're going to do a triangle congruency, is I need to draw segment IO. I'm going to draw segment IO. All right, now, let's go back to where I was at, my train of thought. Sorry about that. I'm going to call this angle 1, and I'm going to call this angle 2. All right? Well, I know by the definition of perpendicular that angle 1 and angle 2 must be right angles. All right, what does that mean? Well, that means that triangle IPO and triangle IQO are right triangles. All right, and then after I drew IO, it is congruent to itself. It's a shared side, and also by the definition of radius in a circle, we know that those two radii would be congruent. So that means segment PI is congruent to segment IQ. Boom. Because of all this, I got right triangles, congruent hypotenuse, congruent legs. The triangles are congruent, so triangle PIO is congruent to triangle QIO. And the reason for that is by HL, right triangles with congruent hypotenuse and congruent legs. And therefore, by CPCTC, I know segment PO must be congruent to segment QO. There you have it. So just showing you how all of this stuff connects to all that stuff we learned about triangle congruency. All right, a couple quick examples. If DG and DI are tangent to circle N, so right away I'm going to mark my right angles. I'm going to mark congruent radii, and the measure of angle IAG, measure of arc IAG, so from here to here, is 240 degrees. Find the measure of angle D. Check it out. If this arc is 240 and all the way around the circle is 360, this arc is 120, which makes this central angle 120 degrees. And in a quadrilateral, all the angles, so here's my quadrilateral, all the angles got to add to 360 degrees. Well, if this is 120 and that's 90 and 90, that leaves 60 degrees for D, because all four of those angles inside that quadrilateral have to add to 360. All right, over here, if the perimeter of this thing is 24, and I know you can't see these, so that's 5, that's X, that's 3, we're going to solve for X. Perimeter is 24. Now check it out. By the ice cream cone theorem, if this tangent segment's 3, so is this one. If this tangent segment is 5, so is this one. And if this tangent segment is X, so is this one. If the perimeter is 24, I'm just going to add them up. So 10 plus 6 plus 2x equals 24. So if I subtract 16 from both sides, 2x is equal to 8. X would be 4. There we have it. All right, and then the last thing here, an intercepted arc. An intercepted arc is an arc that is in the interior of an angle. Interior of an angle. So in the example before, angle GNI, go back, angle GNI, it intercepts arc GI. That is the arc that's inside of it. So that's what intercepted arc means. If you read that, it's just like, hey, the arc that's inside of the angle it's talking about. And then last thing are tangent circles, and these are coplanar circles that intersect at exactly one point. And these are examples. There's two options. You can have externally tangent circles, where the circles are, not inside of one another. Right? Or you can have internally tangent circles, where one circle is inside of the other one. In either case, the circles are still tangent. You just have externally tangent versus internally. So that's it. Good luck with the homework. Let us know if you need help.